equation. So we can just solve it. We have the location of that pole. What do we actually know about the residue of that pole? Well, in order to find the residue of that pole, what we really want to do is fit basically as close to that pole as possible, and you can think about running a little conformal around the distance delta from the pole, but basically we want to go sit on the pole and look at the coefficient of the singularity. We know, of course, that it's linear, the propagator is linear in this squared momentum, so it's a linear pole, so the singularity is z minus dAd, and we want to look at the coefficients of that singularity. Well, so we know what happens when you approach the pole. We get a factorization of the amplitude. And this is no longer at the level of a single diagram, which may or may not be true. This is at the level of the amplitudes. We're summing over all the diagrams. So we know that as we approach the pole here, we're not just getting very close to the pole, kind of the usual factorization. We really want to sit on top of the pole. So we're going to have a singularity here. We're going to look and ask, what is its coefficient? Well, its coefficient, there's a left amplitude and there's a right amplitude. So as we're sitting on the pole, then the amplitude, A of z, is going to factorize. There's going to be a left amplitude corresponding to, let's say in this case, the terms of AO. And there's going to be a right amplitude, and then there's going to be the singularity. Here, we're not getting just close to, we really want to sit right on top of it. So, okay, so what about the residue? Well, of course, that momentum is not going to be flowing through either of these two, so there's no multiple poles. That's, of course, consistent with the fact that in field theory, we get a single pole here. We don't get this thing cubed or fifth power or squared or anything. We get a single pole instead. There'd be trouble with unitarity otherwise in single particle space. So, and we get the pole from here, so basically we just need to extract the overall factors. We can put these factors at the pole, so we're going to get DAD, AL and AR from DAD. And we can pull out a factor. So there's a DAD coming from the fact that our original integral, we're not just looking at the residue of A, we're looking at the residue of A of z divided by z. So that's where the DAD is coming from. And this form is, of course, not of the form z minus z pole, so we just want to pull out this factor in front. So we get z minus A, AD. And finally, there's pole. And of course, if we were, the Laurent expansion has other terms, but we're not interested in them because they have no singularity. Well, so the residue now is very simple. Take lots of factors of I here. The residue is very simple to take because we just take the coefficient of the term in the Laurent expansion. Bingo, there we are. And the other thing we can notice is that CAD times this binomial complex product, well, that actually shows on the denominator, so that product is, remarkably enough, just the naive momentum flowing through that channel. The unshifted momentum flowing through that channel. That thing, of course, is nowhere near a pole. It's just some momentum invariant square, some non-zero quantity. But it's the naive thing flowing through there. So that's the residue. And that's it. So notice that, of course, we've had to factorize at least two legs on one side. We have to have at least a 3-point amplitude here. So each of these amplitudes, AL and AR, has fewer external legs than our original amplitude. So we've written an amplitude in terms of on-shell objects that have fewer external legs. And of course, we can iterate this procedure and ultimately get down to something that just has 3-point amplitude in it. And I'll show you a simple example of how that works next time around. The only twist is that these have to be evaluated at complex values of the external momentum. So they're not the original external momentum. They're shifted into the complex plane by some amount which is determined by this equation. And we can diagrammatically, if we imagine, for example, that J and L are n minus 1 and n, then we can write this identity, this recursion relation, on-shell recursion relation, in the following form. You can label some of the legs, leave the others unlabeled. So this is a simple form where I am taking the suit of the adjacent, although that is not necessary. So now I'm just going to have a linear number of legs. In practice, that's generally a good thing to do because it minimizes the number of terms, but conceptually it's not essential. So we're going to write that in terms of lower point amplitudes that have the product of each term as the product of two lower point amplitudes, the naive propagator. Of course, the thing that I haven't mentioned, but that you have to do, you always have to sum over all possible internal states that can be there. And in our case, even if we're looking at your gluons, that means that you have positive and negative helicity. And the one subtlety is that all these amplitudes, because we're working in the cross language, where everything is nothing goes to n, that means that when the momenta are directed outwards over here and outwards over here, it means they're going in opposite directions. And remember, when you flip the sign of the momentum, you're also flipping the helicity. So the helicities that you're summing over are opposite. So pi actually is equal to, pi is equal to 1, and it goes up to n minus 3. So you start with having a 3-point amplitude over here, you end, the last term of the sun has a 3-point amplitude over there. These are on-shell amplitudes with the external legs shifted into the complex plane, and we'll come back and discuss this a little bit more and do an example and also do a little bit more discussion of factorization tomorrow afternoon. But if there are any urgent questions on, I know I've run over it, if there are urgent questions on the BCFW relations, then now is the time to ask them. So when you have a minus that's just tracking through the signs. When you actually plug this back into to the equation here, there's another minus sign and it'll actually disappear. I mean, there's a little bit of that minus sign cancels this minus sign, so the thing that you ultimately end up with just has I over the naive propagator denominator in the middle here times the two amplitudes.